Now we can talk about inflation itself. Uh, Inflation cosmology is how to give an account of Big Bang itself back to an extreme short instance after the Big Bang, something like uh, 10 to the minus 32nd after the T equals zero singularity. Just to give a sense, this may be compared to the even earlier period, comparable to the Planck time, which you were talking Planck time was 10 to the minus 43 second, which required the quantum gravity for a proper discrimination. So we still can't get away with just GR. During this inflation epoch, the universe expanded in a burst, with the scale factor increases like more than 30 orders of magnitude. So here is a plot of scale factor as a function of cosmic time. Uh, so without inflation, we have this typical power law change. So maybe expanding universe goes like this. But inflation is during a period of time, it just shuts up. Okay. So in other words, without inflation, you would have started a much larger area. Then with inflation, you can start very small volume and to describe the whole universe. Okay, we talked about when you look at this picture, uh, here's the power law, maybe in fair later we'll talk about accelerated expansion, but the point of inflation we're talking about here, when the scale factor just shots up for many orders of magnitude, and before it goes into the standard power law expansion. Okay, so we're talking about this period of time is the inflation epoch. This explosive expansion could have happened if there exists then a large cosmological constant lambda, which would have supplied the huge repulsion leads to the period exponential expansion. And we see this solved the flatness problem, as any initial curvature could have been stretched flat by the burst expansion. This also solved the horizon problem, as such an expansion can cause points in space to separate with superluminous speed. It was separate with speed greater than the speed of light, regions which today, or even at photo decoupling time, appear to be outside each other's horizon, but could still have been connected in thermal equilibrium prior to the, some area that's in thermal equilibrium, then blew up and outside each, so parts become outside each other horizon. So here's talk about inflation scenario proposed. Around 1980, Alan Guth was researching grand unified theory of particle physics, GUTS, which postulated that at energies something like 10 to the 16 GeV, strong or weak electric forces, which are distinct in the standard model, are unified, which means at energy higher than such energies, they're indistinguishable. They're just strong forces, just like behave like weak and electromagnetic forces. And when the gut seems to imply that there would be a cosmic abundance of magnetic monopoles, uh, magnetic charges, in contradiction of their observed absence. And Goose proposed that the early universe, when its thermal energy was comparable to 10 to the 16 GeV, could have had a large cosmological constant, which would have brought about a period of exponential expansion, thereby dilute the monopoles to a very small time. You have maybe a fair amount of monopoles, but suddenly the volume exploded, so therefore its density just diluted to a point that you cannot practice zero. He also realized immediately that besides inflating away the monopoles, this idea provided a framework for solving the flatness horizon problems. In the inflation cosmology, the universe is assumed to have initially been endowed with some scalar field. Scalar means it has no direction, just like scalar quantity. This, at our present age of understanding in particle physics, is purely a hypothetical energy carrying quantum field. We don't know what it is. We don't really have no observation evidence for it. Following particle physics convention, appending an on to a particle field names, so it's often called inflaton field. The fluctuation of this inflaton field is theorized to have possessed a finite time interval, a vacuum state with high energy density, which acted as a cosmological constant that drove the Big Bang. So the idea is that the energy of this contained this inflaton field behaves as if it has a cosmological constant. Okay. So Guth's original model was quite specific, but this effective cosmological constant was related to something called false vacuum of spontaneous symmetry breaking in the Gus theory. Okay, I'll explain all this. And the inflation field was identified with the Higgs field of the theory. Okay, I remember Higgs field is associated with spontaneous symmetry breaking, that can endow particles with masses, just like the Higgs field discovered a couple of years ago in CERN. However, we now view inflation as a general framework whose phenomenological success is quite independent of any specific theory how this cosmological constant was actually generated. While there is no observational evidence for any specific inflaton mechanism, we will present a brief account of the phase transition associated with Guth's original idea of using spontaneous symmetry breaking. The reason we do this is provide a concrete example, especially in the semi-classical language, to see how such effective cosmological constant might have been generated during the inflation period. Because it gives some idea, otherwise just talk about inflation, you don't know what is cosmological constant. The idea that we have this inflaton field, the scalar field, phi, and just like any field, it carries energy. So we talk particular potential energy. In normal cases, you have something like this, the potential energy as a function of phi. And the lowest state is the lowest energy here, we define to be V equals 0. So that's something, that's true vacuum. In fact, quantum field theory, oscillations around this vacuum give rise to particles. Okay? But this potential energy turns out to be, the parameters depend on temperature. When the universe cools, the temperature parameters change such a way suddenly this potential changes to this shape. Okay. Now, first of all, what is this shape? This says this, at least for the simple illustration, this potential has a symmetry property being phi v phi equals minus phi. It was, this is same. Okay, so there's plus minus phi symmetry. But now, when changed to this shape, you still have phi plus phi minus symmetry. It was this still equal to this. But the difference is that this originally the ground state, the vacuum, temporary is here. Okay, so this is no longer the lowest energy state, so no longer the true vacuum. So we call it this the false vacuum, because before long it will roll down to the true vacuum. Okay. Now the whole idea is that this potential of such a feature, that at the false vacuum location, actually the potential is very flat. So it takes a long time for the system to move to a true vacuum. It was the V of phi is almost flat at in this case phi equals 0 point. So allow for a slow rollover transition. It doesn't go right away. So during the rollover period of time, the system here, so compared to here, it has a vacuum energy, okay, which is effective constant. So this is remember, a constant energy term behaves like a cosmological constant. So that's how the cosmological constant is generated. The key feature is the existence of state matter that have high energy density that cannot be rapidly lowered. So that here in this picture is this false vacuum state in a spontaneous symmetry breaking. Spontaneous symmetry breaking means that you have the symmetry uh, 5 minus 5, but once you roll down to uh, one of true vacuum, now this point obviously is no longer symmetric with respect to 5 plus 5 minus. So therefore, you will see if talking about all the other features of theory, it doesn't appear to be symmetric anymore. So therefore, we say the symmetry is broken, so spontaneously broken. We call discussion of time depends of a scale factor in the vacuum energy dominant universe, with cosmological constant. It obeys a rate equation. The a dot, the time derivative of a is actually proportional to a. So it leads to the exponential expanding. So therefore the solution to this rate equation is exponential. Okay. So a equals e to the t some time constant. We should also note not only the scale factor increase exponentially, its derivative a dot also increase exponentially because you differentiate the t on both sides. You just pick up another, just pick a time constant term, but otherwise you still have the exponential term here. As an aside, in such a cosmology, the Hubble constant, in fact, is a constant. Okay, take the ratio of these two. That's Hubble constant. Yes. Now, how to solve the horizon problem? Two fixed points in the coherent space are separate at time t by a proper distance. Okay, and these points receive from another exponentially with speed that also increase exponentially, as I just said. So therefore, the receding speed is actually proportional to this, and the separation, of course, increases exponentially. So the receding speed also increases exponentially. So this receding speed may well exceeding c, because bigger and bigger. But this without violent rule, nothing can travel faster than light in the co-moving rest frame. Okay. Namely, according to relativity, an object cannot travel through space faster than light relative to any local observer, but there's no restriction stipulating the space itself cannot expand faster than c. It was the proper distance between remote observers can easily exceed c. This phenomenon is not unique to inflation cosmology. Any 2 points separated by a distance greater than the horizon length are receding faster than, expanding universe. You go farther away, receding speed is getting bigger and bigger. So you can see when you exceed the horizon length, it will recede faster than speed of light. By allowing such superluminal recession speed, this inflation scenario can solve the horizon problem because 2 points are further apart than their apparent horizon length, whether in the present era or the photon decoupling time, could still have been in causal contact before the onset of inflation expansion. The idea is that during inflation, the space could have gone so fast, so quickly, that the entire observable universe could have been originated from a much smaller region, which in thermal equilibrium. It was without inflation, you would have stopped huge area, but with inflation, the whole universe could start from a much smaller area, and this area, all parts are in thermal equilibrium. And then, but through superluminal expansion, it could go large, and for such separations, they could either be outside each other horizon. It can also solve the flatness problem. Inflation cosmology can also solve the flat problem by stretching any initial curvature of space for all practical to a flat space, because the exponential expansion of the rate. Okay, so remember the Freeman equation written in this form: 1 minus the density parameter equal to 1 over a dot square. So therefore, the ratio of this 1 minus omega in 2 times t1 t2 is equal to uh, uh, t2 t1 dot ratio squared, and which by this factor here is minus e to the delta t over tau time constant. Okay. So for example, just suppose the scale factor inflate by a factor, say 30 orders magnitude. The right hand side of this equation could be as small as 10 to the minus 60. So if we start with any reasonable value of omega 1, whether it's doesn't have anywhere near 1, but we can still have after inflation, which is at this point T2, with the omega, basically this goes to 0, so therefore omega has to be extremely close to 1, to a high position. So in other words, gravitational attraction slows expansion universe to a decelerating universe, enhancing its curvature while driving the density away from the critical value. So that's the flatness problem. But the accelerating expansion due to vacuum repulsion always pushes the universe very rapidly towards flatness, omega to 1. So therefore, a firm prediction of the inflationary scenario is that the universe left behind the inflation must have a space with a flat spatial subspace of the space-time. The 3 states must be flat geometry. And I remember in the last lecture, we said that the firm prediction, which was made in the 1980s, of inflation cosmology having a flat geometry was supported by observation in the mid-1990s of by the observed cosmic microwave anisotropy, which has angular spectrum. The first peaked at the multiple number 200. Remember, the factor peaked at 200. Since its geometry is flat, so so we do indeed live in a flat universe, as predicted by inflation. But according to Einstein's equation or Freeman equation, such a geometric property implies a critical density, in which density must equal to critical density, so you got omega equal 1. This seems to appear contradicted by observed matter density. Even including dark matter, we still have only almost a third of 0.3. So short of the omega equal to 1 prediction of the Freeman equation. So although the theory predicts omega naught should be 1, it does not specify what component makes up this density. As we will see, the apparent contradiction will be resolved with another invocation of Einstein's cosmological constant. So that's the second part of lecture 28.